Hi everyone, welcome to a new series of videos that will explain the new capability that has been built within the Moose framework for DCS World, and this is around finite state machines. Within this video we are going to explore together some of the concepts that define finite state machines, so that you'll understand better the in-depth demonstrations and how to utilize ready-made classes that use finite state machines. This is an example of a finite state machine, graphically represented. The white boxes are states, the blue boxes are events, and the red boxes are sub-finite state machines. Now, a finite state machine defines the rules of transitioning between those states triggered by the events. In another word, a finite state machine describes the rules when an event is being fired. So when the update event, for example, can transition from the state machine from the state arrived to the state updated. So the finite state machine during execution will transition between the states. So it will go from planned to accepted to arrived to updated, and the events are executing the transitioning. Now, it could very well be that an update event has been fired, but the finite state machine was still in the accepted state. So the event transitioning won't happen. Would actually be an error. But if the state of the FSM would be in arrived and the update event would have been fired, then the transitioning can occur, and the result of the transitioning will be that the finite state machine will be in an updated state. So in summary, the state, the white boxes, define the moment within the finite state machine process. The blue boxes is an event describing an action, and that action can be triggered within the process both internally as externally, and I'll come back to that later. And the event can be triggered, so they can be, because it represents a transition, this event can be triggered or embedded within the state machine or delayed over time. The sub is actually something I'm not going into details right now, because we need to go through a couple of examples before this can be understood. But basically, you can remember right now that a sub facilitates the reuse of ready-made finite state machines, so that the wheel does not have to be reinvented every time. So let's talk about transitioning in a bit more detail. When a transitioning happens, so when it can be executed, during the transition execution, there are actually 4 moments that are being evaluated during the transitioning process. And those moments are on leave, on before, on after, and on enter. On leave is the moment when the finite state machine leaves the from state. On before is the moment before the finite state machine is processing the event. On after is the moment when the finite state machine has processed the event. And on enter is the moment when the finite state machine enters the to state. Each moment can be catched by methods that will be called by the finite state machine while executing the transition. So the mission developer within his script can create methods with a certain naming convention that will be called by the finite state machine, and you can then embed within those messages your own code to be executed that will become part of the state transition process. So you can catch state transition moments by creating methods that are starting with the syntax onLeave or onEnter, concatenated with the state name. So in this example, onLeave from would be called when the transition would happen in moment 1. onEnter to would be called when the transition would be in moment 4. You can catch event moments by creating methods that are starting with onBefore or onAfter, concatenated with an event name. So onBefore event would be called at moment 2, and onAfter event would be called at moment 3. Now, something else that's important to remember as well, that is that moment 1 and 2 are actually conditioning the transition to be executed. So those two methods may return the boolean false to cancel the transition. So within your code of the method onLeave from or onBefore event, you can build in a return statement saying return false, and once a statement has been executed, this transition will not be executed. But when you return true, then the transition will be executed. Yeah? So a finite state machine process is actually being executed by handling these event transitioning moments and develop code for the onLeave, onBefore, onAfter or onEnter moments, like is being shortly explained here. So you build a function, finite state machine double point, for example here, onAfter and then event 1. So you use the name of the event here and concatenate it with onAfter, and this will then be called at moment 3. And within that function you can then use of the finite state machine two different event functions. And the first event function format is very simple. It's just the finite state machine double point and then use the name of the event that has been defined within the rules. You can even add optional parameters, or you can call the event delayed, which is the same ways. It's finite state machine double point and then two underscores and then the name of the event, and then between brackets the first parameter will always have to be the amount of seconds that will be waited until the event transitioning will be executed. Okay, so let's summarize. An finite state machine embedded event call is actually a call that will call and execute the event transition immediately, while a delayed event call is executing the event transition after X seconds, and that parameter is given as a first parameter of the function. Okay? The distinction when to use embedded or delayed event triggering is subtle but important. So as you will understand, delayed triggering is actually resulting in better performance because the processing of the finite state machine will be chunked into pieces when a transition happens, while embedded calling allows better handling of memory, and it will also allow better handling of sequencing of events. But you'll experience that when you start using finite state machines later during your mission design. Okay, let's get to an example, and what I'm going to do is I'm going to take the AI Patrol Zone class to demonstrate the finite state machine implementation. So here I am. I have opened the test mission, which you can find within the Moose framework under the test missions section, and I went to the patrolling test mission section, PAT001, switching patrol zones. So this is a small demonstration that explains one of the powers of finite state machines. So you can actually build a long-lasting process using a small amount of code. So let me explain this code very quickly. Basically, I've defined a patrol zone. Actually, what I've done is I've added within the mission a patrol zone 1 group, which is basically like a path, a route, right? And for that, I suggest you refer to the patrol zones explanation within a previous video, which I will rework later anyway. So basically, I create a polygon zone here based on the group defining the patrol zone using its path, and I do the same for patrol zone 2. Yeah, so I create 2 patrol zone polygons here. And what I'm going to do now within this small mission, I'm going to spawn a patrol group, let's say spawn object, and I'm going to spawn planes that are going to patrol within the 2 zones. But what I'm going to do is I'm going to let take off a plane from an airbase and is going to fly to patrol zone 1. And when it returns back and lands, then I'm going to instantiate a new airplane that is not going to patrol in patrol zone 1, but is going to patrol in patrol zone 2. And using a finite state machine capability, I will switch between patrol zones. Now the AI patrol zone class is actually an already implementation of a finite state machine. And when an airplane is flying around and gets out of fuel, the return to base state, or sorry, event will be raised, right? So when the RTB event is being raised, is being triggered within the AI patrol zone, we can catch that event using, as I explained, the on before RTB or the on after RTB. All right. So now here's the nice trick. So I create a patrol zone, and for that we'll need to get into the AI patrol zone mechanism later, but basically what I'm doing here is I am creating an AI patrol zone finite state machine process, and I tell to the patrol zone when they are patrolling that, you know, when the fuel is less than 20%, then return to base. And I say to the patrol zone, manage the patrol group to patrol the zone. So in other words, by this statement, the plane patrol group will start patrolling within the patrol zone and start within 5 seconds. Look at this. This is very interesting. So when you check the AI patrol zone finite state machine implementation, you'll find a start event in there. So let's get browsing into that. This is the definition of the AI patrol zone, and this is actually the creation of the rules, and you find this start event here that is being defined as a transition. So I can call the event start, but in a delayed mode, right, during my mission. So I'm saying start AI patrol zone 1 within 5 seconds. That's basically what this thing says. So then the patrol zone will start, it will be executed, it will route the plane will fly around within the patrol zone, but when it gets out of fuel around 20%, the RTB trigger will be called. Let's look how that looks like. Excuse me. Let's have a look. Sorry. So here there is a transition defined, RTB. So when it is patrolling and the plane gets out of fuel, it will call an event or raise an event, RTB. And we can catch that event here. What I'm doing here is when the RTB happens, before the process happens, I am sending a message to the red coalition saying I'm going to return to base, and I'm showing that for 20 seconds. So we go here back. So let me explain what happens here. So it's really during that transitioning, when the event RTB is being executed by the AI patrol zone class, then the on before function is being called that you can catch. So This one I'm doing here. And then on after RTB, so once the message has been sent and I've executed that event, I'm going to do something else. I'm going to create a new plane, right? Using the spawn object. I'm going to say to patrol zone 2, control that plane, that new spawn plane, and start within 1 second. So the old plane will return to base, while the new plane will start patrolling now in patrol zone 2. Okay? And then basically what I'm doing here is the same. So here I'm saying, okay, when the patrol has been finished, going RTB for plane 2, I'm saying I'm going to return to base, and when the RTB event has been executed during the transition, I'm going to spawn a new plane. I'm going to say to patrol 1, start within 1 second and start patrolling. Okay, and once the patrol, which is another event, let's look what that looks like within the class. So when you got patrol, so here is patrol being executed here, right? So when the state is patrol or route, the patrol can happen and it will get into state patrol. So when that event patrol is being executed by the AI patrol zone class, then this will be executed on after patrol, and I'm sending a message. So that AI group is going to send a message to the Red Coalition saying, look guys, I'm patrolling in zone X. Now let's have a look how that runs within DCS world. Alright, a short demo. So what you'll see is that this plane is currently being spawned. It's being ordered to patrol around here, and once it gets out of fuel, it will say to the patrol zone, I am out of fuel, RTB. The on after RTB will be called, that method, remember, here, and new planes will be called. So that method will be called here, this one, new group, and start patrolling for patrol zone 2. So let's go back and accelerate a bit so that this plane is taking off. Right. So now you see the plane patrolling in area number 1. There you go, it's turning around. Okay, now we're in a moment where this plane is saying, I'm going to return to base, and I'm going to orbit at the place for around 60 seconds, and then I'm going to return to base, while this plane is now taking off and is going to patrol in patrol zone number 2. Now this is really powerful. So what we built here is a switching mechanism. Plane 1 starts, flies around here. Once the plane is out of fuel, it will orbit for around 60 seconds, return to base, and plane 2 will take off, will orbit around here. Once that plane is out of fuel, it will orbit for 60 seconds, return to base while plane 1 is taking off. So in this way you can actually build continuity within regions, so planes being patrolling a certain zone without having no plane within that zone. That's the basic mechanism of patrol zone. Yep. Now we can add within those methods, while patrolling we can actually add other functions or even other finite state machines to actually control that AI while patrolling. Like it could say, I'm detecting other planes, and once I detect a plane, I could even trigger another action that needs to be executed using the finite state machine. So I invite you to execute this little demo here and see how this works. And I hope you like this demonstration and the new capability of finite state machines that will be implemented extensively within the new MOOS framework. So I hope you enjoyed this little session. You can find the MOOS framework links on the Eagle Dynamics forums. You can even send me a private message. My ID is Flight Control. Or you can reach me on Skype. Or you can even join our slack.com community using and developing the Moose framework. So feel free to use this framework. It's public domain, and I hope the finite state machine capability is providing a lot of dynamism and a lot of new ideas for mission designers to start developing missions. Bye bye.